Good evening. I'm Mark Marley. I'm the director of the Lunar and Planetary Lab here at the U of A. And we're so glad to have all of you here. Every year, we give three evening public lectures to tell folks about the kind of science and all the exciting things that we do here at LPL. And we try to have a theme every year. And I was trying to think of what the theme was going to be for this year. And then on my playlist, Belinda Carlisle's Heaven is a Place on Earth came up. And I was thinking, well, there's so many people at LPL where space is a place on Earth that works to study processes and things that are happening in space by looking here on Earth. And so that's our theme this year is how do we better understand geologic processes all around the solar system by studying Earth. And so this is the second in our lecture series. We're going to hear about studying glaciers on Earth and how that can help us learn about Mars. And then the third lecture is next month, which is more of an astrobiology theme and understanding life processes here on Earth and how we can use them, understanding of them to help us understand the search for life in the solar system. So we hope you'll come to that one too. So tonight, it's my pleasure to introduce Professor Jack Holt, who is a professor both in the Department of Geosciences and the Lunar and Planetary Lab here at the U of A. Jack got his bachelor's degree in electrical engineering from Rice University, and that background I think helped a lot in the kinds of science and radar systems that he's doing today. And then he went on to get a master's and PhD in geology from Caltech in Pasadena. He's had a varied career, lots of interesting places, doing interesting things, including time as a research faculty, as a research professor at the University of Texas at Austin Institute for Geophysics. He joined LPL back in 2018 and has been here ever since. He uses radar methods to study glaciers on Earth, as I said, for its own sake and also for a better understanding Mars, including flying his own plane, which I'm hoping we'll hear more about. This led to him proposing a couple of years ago a mission, well, kind of not a space mission, but an Earth mission to fly radar technology around on Earth to study glaciers and called Snow for Flow, and we'll be hearing about that. So I'm going to turn it over to Professor Holt. And if there's any students here for extra credit in your class, at the end of the lecture, you can go out and sign the sign-up sheet at the desk up front. So take it away, Joel.
Thank you, Mark. Appreciate the nice introduction, and thank you all for coming out on Wednesday night in Tucson to hear about glaciers. Curious how many of you have seen a glacier in person? That's a lot. That's great. How many of you have been on a glacier, walked on a glacier? Dang, okay, we're done. Don't need to know anything. People often ask me why I'm studying glaciers in Arizona. I'm like, well, I study glaciers on Mars, so be anywhere to do that. All right, we're going to talk about glaciers, and if this works, it will not work. Yes, but this should work. I would first like to introduce current members of the Taper Lab. Stefano Nerozzi, research assistant professor, has been working. I've been working with him for a long time. Michael Daniel, graduate student. Roberto Aguilar. Anything you see in here about drone radar, it's Roberto. Reed Sperling, who was an undergrad in the group, but now is a research assistant. So what is a glacier? Basically, a lump of ice that is flowing downhill under its own weight. I do want to see if I've got a laser pointer. This thing. I feel like the batteries are dead on this, or there's an on-off switch that I'm not getting. They're on-off switch. Yeah, that degree in electrical engineering is coming really handy right now. Well, yeah, that works. It better. All right, well, there's we can fix that. So sort of some things to remember about glaciers. There's an accumulation zone and an ablation zone. in between, the thing that defines the boundary between that is the equilibrium line. Basically, you have snowfall, usually over the whole glacier during the course of a winter, but the snowfall that remains through the summer becomes part of the glacier. That's in the accumulation zone. Below that's the ablation zone. You have melt, water that either evaporates or runs off, and then you have calving if it's going into a lake or an ocean. And mass balance is kind of a health check for a glacier. It's the difference between the accumulation and the ablation. If those things match, then it's in balance. They almost never are. If it's positive, the glacier is growing. If it's negative, it's shrinking. And sometimes, like currently for a lot of glaciers, the equilibrium line is moving up higher in the glacier, which reduces the accumulation zone, makes it typically more negative mass balance. All right, so just talking about mass balance, at least for Alaska, this is a map of all the glaciers. Everything in red to yellow is negative mass balance, meaning their glaciers are losing mass overall. And so I've done a lot of work in Alaska over the last 10 years doing measurements to help refine these estimates and improve our projections. A lot of assumptions built into that, but they're definitely retreating. Just a few photos. I could spend the whole time just showing pictures of glaciers in Alaska, but well, maybe we should. You want to do that? That might be better. So this is just the typical flying along in Alaska, a bunch of glaciers in the mountains, and notice a little debris flow or landslide that came out onto the glacier and then now get carried down on it, which also changes things sometimes. You got it? I think so. Excellent. Thank you. Yes. Okay. Just a couple more examples, a couple smaller glaciers. One kind of big, a lot of tributaries merging, making these medial moraines that flow down. See a little bit more of that coming soon. The accumulation zone is kind of a sleepy, quiescent area when you're up there flying, doing measurements. It's just really nice and peaceful. Usually not much going on, maybe a few little crevasses here and there. And then you start going into where it starts dropping off and moving faster. The ice is experiencing stresses and starts getting stretched out, causing crevasses to start form. Then down in and that's another example of kind of an intermediate zone. Can get really messy. This glacier was actually surging just before we went over it, so it's really broken up. And then down in the ablation zone, it can get a little messy. I guess the audio is coming through on the system, but it's just the sound of an airplane flying. So, yeah, so this is down at the terminus of Hubbard Glacier, which calves into the ocean and a bay. It's really cool. Those ice cliffs there at the end are about 500 to 600 feet high for scale. Pretty so right up in there, something just capped in and creating waves all out into the bay. This almost always capping something. All right. Why do we study glaciers? Well, important part of the climate system for one thing. They're changing rapidly everywhere, pretty much retreating everywhere. In order to understand how rapidly, we want to understand how rapidly they're going to contribute to sea level rise and impact coastal ecosystems. They can make big changes to the ecosystems, and I think they're just pretty darn cool. How do we study them? Typically, a lot of it's done from space, but not everything. You can measure velocity of glaciers from space using cameras, imaging radars, by looking at change over time of the surface, tracking features, and laser altimeters that measure the surface elevation and monitor what their surface lowering or inflating over time. But you need radar sounders to see below the surface and to measure things like ice thickness and how much snow is accumulated. That's kind of my specialty combined with the other techniques. We always put a laser on the plane to measure that as well, to measure the surface. And that's usually on low flying aircraft or on the surface itself. So I'll be talking a bit about radar sounding, so we need to have a little review. And there will be a quiz later, so to pay attention. So basically radar sounding, it's like, police radar is very high frequency. They point it at you and get a speed. This is very long wavelength energy. So like 3 meters or more, usually penetrates freshwater ice very easily. In Antarctica and Greenland are pretty easy. It's really cold, dry ice, and it's very smooth on the surface. And so I've used a plane like this, DC-3, that's modernized with antennas under the wings, producing 5-meter wavelength radar, and it sees through, in this case, 3 kilometers of ice. And you can see the surface and then reflections off internal layers in the bed. So you're sending out pulses of energy very rapidly as you're flying like as many as 6,000 to 10,000 pulses per second. And you're waiting for that energy to go through and come back, and you're recording the echoes. And so that's basically how it works. It's pretty simple. And then notice the power drop off. There's a big surface reflection, and then the little reflections off the internal layering, which are caused by impurities such as dust or changes in chemistry that result from our particulates in the atmosphere over time. And then down at the bottom at the bed where the ice hits the bedrock, and you get a big strong reflection, especially if there's water down there. So that's kind of what we're looking at and looking for when we're doing radar sounding. However, mountain glaciers like you have in Alaska are really challenging. And I'm bringing all these things up because they do end up having implications for Mars at some point, also just because it's fun. So we developed a much longer wavelength radar sounder. It's 60 to 150 meters wavelength to sound through really crevassed, warm, and wet ice like this. The radar sounder I just showed you for Antarctica just wouldn't work here. So we usually operated it on this plane and Otter, and there's some of the radar equipment with my former student, Michael Christopherson, operating it. And we actually feed the antenna out of a hole in the back of the plane. As we're flying, once we get airborne or get up altitude, which you use it that high, we feed it out the bottom, the little drogue on the back, and that's the antenna is inside this rope. And then it just cruises along behind us. You can sort of see it here behind the Otter in this view from a camera that's off on the wing, but it's pretty hard to see usually. So I'm going to show you a couple examples. The first is Malaspina Glacier. It's a really big glacier on the coast in this part of Alaska. It's the St. Elias Range, really massive mountains. You'll get to see some more pictures of that shortly. But a lot of ice is here. In fact, this big ice field here, the Bagby ice field, is the 3rd largest ice mass in the world after Antarctica and Greenland. Malaspina Glacier, I'm blocking it a little bit here, sorry. It's a Piedmont glacier, which means it flows out onto a plain. It's not really confined by valley walls out here in the main lobe, and it's about 50 kilometers wide. We started noticing a lot of melt in the forelands that separate the glacier from the ocean, just barely, and things changing, melting, connections between the ocean and the glacier starting to happen. And so we were concerned, we're interested in what's going to happen. And so we got a project funded to study that. So to give you a sense for how big it is, you all are familiar with this, right? Tucson. I'm going to fade in Malaspina Glacier at the same scale. That's how big it is. It would cover the whole valley. Fade it back out. So there you go. It's a big glacier. We're going to take a little flight over it, sped up, so it doesn't take too long because it takes a while to fly over this thing. So you can see the forelands that are melting because there's ice in the subsurface there. And we're going over the main part of the lobe. You can see where it comes in from the mountains up here. This mountain right there, just for reference, is 18,000 feet high, Mount St. Elias. So twice the height of Mount Lemmon, and it's right here next to the coast. So really insane topographically. All right, so here's some radar data over Malaspina. It's very different than that Antarctic example I showed you. Basically because of the long wavelength, it's lower resolution, but it goes through all this messy ice. So you see a surface reflection and then a bed, and it's drawn out here, picked in some software so you can see the bed picked nicely. We've got about 800 meters of ice in the middle. That's a lot. And note that this is in travel time. It's two-way velocity, so the geometry doesn't represent reality quite because the radar waves slow down in the ice, and so this is all delayed. But anyway, that's how it works. That's some nice data. Malaspina works pretty well. So we flew a lot of lines over Malaspina, basically a big grid over multiple years. Actually, we went back and did more and more each time. And then we can turn those grids of bed elevation, which you can see by the colors, go down up to about 500 meters below sea level, right off the coast, right leeward coast. And the ice thickness up to almost 1 kilometer in the central portion. You turn those into grids by interpolation and see a better picture of what it looks like. So you kind of get a three-dimensional sense of both the bed elevation and the ice thickness. So one of the things that jumps out is this big kind of trough down the middle, and there's multiple other troughs here. And so basically when the ocean starts interacting with the ice, melting back, it will reach these troughs very soon and basically you'll get ocean water into the deepest parts of the glacier very rapidly, which will cause a runaway effect of calving, ice loss, ice acceleration, or melting. And so that's why we think it'll be kind of a catastrophic retreat. But before we had these data, we really had no idea what it looked like underneath. So it's kind of unveiling, taking off the ice, seeing what you have underneath, how thick it is. And then, so it's kind of like making a complete picture. And in this case, this is from my former student, Brandon Tober's thesis and paper. And he calculated hydraulic potential or pathways that water would potentially flow underneath the ice, which is very useful for understanding the dynamics and doing the modeling in a numerical model to predict the future state of the glacier. So this is, just keep this in mind, like this is like the best we have for Earth or these kinds of glaciers. Like this is the best example of a big mountain glacier really extensively mapped with radar. There aren't many that even approach that. All right, real quick, just for comparison and to talk about debris cover a little bit more, we're going to jump inland to the Wrangell Mountains and look at Kennecott Glacier, one of my favorites. It's a very big glacier that it's right near the town of McCarthy. So zoom in on the much on this fuzzy image. But you can see the area per scale, it's 3,500 feet on runway. There's a growing lake in the front as the glacier retreats. Notice a lot of debris as all these moraines coalesce and start covering the glacier. So I'm going to show you a couple of pictures of what it looks like up close. This is flying over the central part, looking up. So you can see the moraines coming down from tributary glaciers emerging. There's little superglacial channels. It's very extensively covered. See some ice through. It's not super thick, it's everywhere, and it's very rough surface. But our radar can see through all of that. We've flown some with the airplane, but we did a more extensive survey last year with a helicopter-borne radar where you mount the antennas on this big platform and then you tow it. Basically, the helicopter picks it up and just slings it. And they can fly slow and even lower and get closer to the valley walls with this. And so we were able to create a pretty extensive coverage map of the bed of Kennecott and Root Glacier on this side, which the state and the Park Service were actually interested in because this is all within Wrangell-St. Elias National Park. And so they wanted to see, well, what's the glacier going to do in the future as it retreats in terms of facilities, access to hiking trails, all these kinds of things. And what we found is interesting, like we kind of expected the deepest part of the glacier would be right in here, have these two converge, but now it's kind of here side and it wraps around over here. And there's also every summer is a little lake up here that drinks under the glacier on the bottom, and it's called a Yakup. You maybe have heard of those. It's not a real big one, but they're concerned about is it going to get bigger in the future or not. And so our data are providing the needed constraints for that. All right, so North Polar Cap, what it looks like. I've done a bunch of work on that. We're not going to really talk about it. But if you melted it, it would cover the whole planet in 9 meters of water. So like basically 30 feet of water across the whole globe. That's a lot of water. Yeah. And if you plopped it on Texas, it would pretty much cover the entire state in 1.5 miles of ice. And I've lived in Texas a long time, and I kind of think that might be an improvement. Just kidding, it's great.
The barbecue floats.
Yeah, if you can get to the barbecue, we're good. All right, so high latitude ground ice, we've seen it visually, excavated by the Phoenix lander, which was UA-led mission. It both blasted some tops, basically regolith off to expose ice by the thrusters when it was landing, and also the scoop exposed some ice that then sublimated away. Middle latitudes, we're going to focus on that. As early as the Viking images in the 70s, people identified these things that they called debris apron complexes. Lost my pointer. And postulated what they were, these kind of, we're going to look at this feature again with newer data real shortly, so keep it in mind. So there's these sort of apron, smooth, lobate things surrounding mountains, abutting steep slopes. And they thought, well, there must be some kind of a flow, like a debris flow or something. There are other Viking era discoveries that you might have heard of based on Mars, but with better data, you can see that actually it's not a face. It's just a mountain that looks like a face at low resolution with sun angles right. So bummer, but oh well. So better data for the same feature we were just looking at. This is ESA mission called Mars Express. They have a high resolution stereo camera. And so it's the same feature, but you can start seeing all these like linear features and curvy features that all indicate some kind of a flow pattern. There's a little thing coming off the side here. So it definitely looks like flow feature, but it's too cold in the current climate for ice to really flow. It's not going to move. There's a bunch of viscous flow features at the mid latitudes of Mars. Speaking of water. So that's what we were just looking at, typically called the lobate debris apron. Concentric crater fill, lineated valley fill, which is probably more like what you would expect for big valley glaciers. And then these little guys, which look like little side glaciers. But if we don't know what's in there, we call them a glacier-like form. And there's so many acronyms for these things, it's ridiculous. I've tried to spare you, but over the years, people call them different things and they have different acronyms, but basically they're viscous flow features. So here's a map showing their distribution in the mid latitudes, thousands of them, of the different types. I've been focused on the lobate debris aprons because they're more like glaciers. And we're going to jump to one in Euripus Mons, in the southern hemisphere called Euripus Mons, and it's kind of a complex of viscous flow features that merge together. Don't hold me to this exactly, but it's pretty close to what Tucson, well, by Tucson next to it for scale. These are big. And so, a lot bigger than Malaspina Glacier, which is already a really big glacier. So we're going to zoom in on some imagery from the CTX instrument, which is on Mars Reconnaissance Orbiter. And as you go in, you see more and more detail of these flow features. It looks like somebody poured molasses on the table and it piles up and starts oozing out. You've got the lineations, the curvy features, you've got lobate fronts. But you also have craters, and they're not formed. So if this were flowing recently, things would be stretched out. A little perspective view, I like these. So same features from the side, you get the front. Nicely. And we're going to do a flyover plan that you can pretend you are using data. We're over the flow feature here, and notice there's not many impact craters. And then when you get to the edge out in the plains, there's many more. It's a much full surface sitting there getting blasted for a long time. Go back on it, you can see the ridges, flow lineations, things like that. Very different. You can tell it's much younger surfaces. But it's also been sitting around a while. You've got some interesting patterns. There's an impact here. So they're not super young, but they're a lot younger than what's out there. So And actually, even though we only saw one or two impact craters, there's enough impact craters on these features in general to indicate that they're hundreds of millions of years old. Question. To get the pitch vector, these, oh, minutes?
Minutes?
Yeah. What was it, like 7 minutes? I don't know. What's the delay? Yeah. It's not much. Sorry, I'm chilling the light so I can see you. Yeah, there's not a huge delay from Mars. Maybe I'm wrong. Maybe it's more, but it's not much more. It's around that. Yeah. The biggest thing is they'll store the data and then wait for the space to be in the right place to beam back to Earth. And that might not be immediately. But if it's real time, then it's on the matter. All right. So what are these? This was a debate for like 40 years. Either the first and favored hypothesis for a long time was debris flows, or we call them, rock glaciers on Earth, with a little bit of ice, and the source of the ice would be slow diffusion around to the atmosphere, and the water ice could be gone, just leaving the rock left. Or the second hypothesis is debris covered glaciers. So essentially glaciers that are formed by snowfall that builds up into ice like you see on Earth. And you would also require that ice to still be there to maintain its shape, but nobody thought that could really work with the current climate because it doesn't, so it didn't get much support. So what's the problem with glaciers? I already kind of said this a couple of times, I guess, so we don't need to spend a lot of time on it. But basically, it doesn't make sense given the current atmosphere and climate. So, however, people smarter than me have figured out how the planet's orbital parameters change over time. And they do these calculations that include all the planets interacting. And you can demonstrate that Mars has, Mars's orbital parameters vary a lot over time, much more than Earth's. So the obliquity is the spin axis tilt. So how much is it tilted from the plane of the ecliptic? Earth's variations are in this blue line, just like a degree or so. And those cause big changes. But Mars, it's all over the place over time. This is over 10 million years. Currently, they're pretty close, like our spin axis tilts are almost the same. But the idea is that at low obliquity like now, the poles don't receive much sunlight. And so the water ice is mostly stable at the poles. But at really high obliquities, which can get up to 35, 45 degrees in the past 10 million years, water ice is more stable at mid-latitudes than the poles. So glacial periods on Mars just mean the ice is moving around, moves from the poles to the equators or mid-latitudes and back. So if you can trap some of that ice at the mid-latitude by covering it with debris, then it could stay there and persist for a long time. So how do we answer that question? Radar sounding, of course. It's the answer to everything, right? Not really, but it's fun. So Mars Reconnaissance Orbiter, MRO, has a radar on it called the Shallow Radar, or SHARAD, built by the Italian Space Agency. And it was designed to probe the top few hundred meters of Mars. That's hence shallow, because there was already a radar at Mars that was designed to go like kilometers depth. So this was the shallow one. And for the quiz later, make note of the 20 megahertz, 15 meters wavelength. So remember the first one I showed you for Antarctica was 5 meters wavelength. The one we use in Alaska is like 100 meters wavelength. You just say that. And it started operating in late 2006 when MRO got there, and it's still going. We still do data requests. So this is one of the first radargrams or radar data we got across any one of these features in the mid-latitudes of Mars. I targeted it, see what's going on. And so really wasn't sure it would work because you're 300 kilometers up. You're not like 500 feet up like you are in an airplane over Alaskan glaciers or Antarctica. But lo and behold, as you're crossing into the plains, you're getting a surface return. This is some clutter out to the side. Don't worry about that. And then when you get over the feature, you get a really sharp surface return. and then an echo from the bottom. So it kind of reminds you of like the Malaspina radar data, right? Yeah. And then the same on the other side, you get the surface and then you get the bottom. And you don't get anything where the mountain is because it's too steep and it reflects the energy away from the radar to go back. So that's in time delay. This is in depth and water ice. We see this wherever we cross these things. Sharp surface echo, sharp basal echo, nothing in between. And we've done a lot of work to quantify the velocity of the radar waves and the power loss, like I showed you that plot for Antarctic ice, to show that these things are essentially pure water ice with a thin layer of debris on top. When I say debris, I mean dust, rocks, whatever, not like car parts. Maybe in Alaska there's car parts. So, paper by former student Eric Peterson, analyzing hundreds of these things in the northern hemisphere and doing all the statistics on the velocities and the losses, showing that they're basically very high purity ice, like 80% and more hot water ice in these. It's a lot of ice locked up in these mid-latitude glaciers. All right, so what do we know about the glaciers? The radar properties, for the ones we're looking at, which are kind of large, are consistent with the debris covered glacier hypothesis. The debris layer, just based on the fact that we only see a surface echo, a single one, we don't see like the top of the debris and the bottom of the debris, has to be sort of 10 to 20 meters thick or less, because that's the resolution of the radar. And since there's all this ice, they must be remnants of a past climate that is favorable to glaciation at those latitudes. So they're not a product of the current climate on Mars. And then also that this relatively thin layer of dust and rock can preserve ice for hundreds of millions of years, which is pretty awesome. All right, but Sherrod, it's amazing. Still going, it's strong after 18 years, 19, I can't do math, but it is limited. You know, it was designed to go deeper into the subsurface than we're often trying to see. So its horizontal resolution or its footprint can really, we can only study features that are about 10 kilometers or so or bigger across. And then vertical, 10 meters, kind of the thinnest, highest resolution. And if right near the surface, you can really only resolve things about 20 meters. Lower, deeper than 20 meters. So a lot of people are interested in really shallow ice on Mars, trying to get to it with a drill or something. But if you say you don't know if it's less than 20 meters down, they just laugh at it. The engineers need better numbers than that. We also, they're basically, this is just another example of crossing some of these, and that's the depth corrected version right there. We don't really see anything inside. We don't see internal layers, and we think they're there. This is an image from a paper showing, basically this is topography, HiRise, the camera that U of A runs, built and runs on MRO, showing these layers on the edge of one of these viscous flow features, and the little community fed into it. There's evidence that there's layers in there. We can't resolve them with Sherrod, so we'd like to. All right. So what do we not know? What do we want to know? How does that top layer form? What are its properties? How thick is it? Is it variable? How did these glaciers flow? Was it just super slow over 100 million years or more? Or is it episodic at times? Or did it all flow at the beginning when it was first formed and then it stopped? We really don't know. We'd like to be able to look at surface morphology like the ridges and say something about the flow history, and then hopefully invert that for its sort of accumulation history. Did it all form at once? Or did it form, over multiple obliquity swings? We don't know, but there's other reasons to study Mars ice as well. As I mentioned, people want to get to it as a resource, so they want to drill into the near subsurface and access it to support people and make rocket fuel. There is evidence that there's ice in the near subsurface. This is another HiRise image of an icy scarp That's something we cannot resolve with Sherrod. There's definitely ice in there. But we can't map it with a radar. And so there's probably a lot of ice in the near subsurface that we can't see yet. And then astrobiology reasons, this is a concept called Mars Life Explorer. It was a high priority mission in the last planetary science decadal survey. So there's a lot of reasons to study Mars ice besides glaciology and paleoclimate, but they kind of have the same goals. All right, back to Earth. So when we discovered these things were essentially debris-covered glaciers on Mars, I thought, okay, I'll just go to the literature for Earth debris-covered glaciers and rock glaciers. It's kind of the same spectrum of things, and see what people know about them. And it turns out they don't know much. This is Sourdough Rock Glacier. We're going to be seeing a bunch of stuff from that soon. And this is about the same scale as this. So this is about 2 kilometers long and about 1 kilometer wide on the toe. It's about the same scale for this glacier-like form on Mars. So they look kind of the same. People have always called this a rock glacier. You can't see any ice anywhere, but it clearly has flowed and caused all this flow morphology. So, whoops, sorry, it's happening, delay. All right, back. So like I said, people didn't really know, have any answers because these things had not been studied in any detail on Earth. So we were like, well, okay, I guess that's what we got to do. We can access these things. This is one in Wyoming. We worked out, talk more about one that's right next to it in a little bit. So yeah, we just wanted to answer some of the same questions, like how much ice is in there? When did it accumulate? How thick is the debris on top? If it's a debris covered glacier, we didn't know when we started out. And what are the processes that influence its flow and evolution? And is there a climate signal in all this crazy morphology? So that was like 10 years ago. Took a few years to get funded to do it, but finally did. The methods have been mainly ground penetrating radar. So again, radar sounding, but using instruments on the ground like this, or towing them on a sled, and I'll get to the drone stuff in a bit. Also repeat photogrammetry, because we can go out like maybe typically once a year, do photos and look for change and quantify it. We've tried a bunch of techniques to see what's good. We've done some seismic, but I'm not going to talk about that today. And some other methods. All right. Back to, for context, that's Sourdough Rock Glacier in Alaska. First one I showed, McCarthy Creek Rock Glacier. I put it on this for reference to Kennecott Glacier, which we were looking at earlier, for scale. These things are not very big compared to one like that. But it's pretty accessible from McCarthy, and so that's where we started working first time. And there's just a little shot just flying past. The lighting was kind of good. You can see the flow morphology coming out, Sourdough. And it's pushing trees down along the edge, so we kind of knew it's pretty active. There's like trees like leaned over. Just a little more on the personal front, right here by the airport. Have a little yurt. Hang out in there sometimes in the summer, as much as I can, between research projects or just working from there. Just hidden in the trees. People are always asking me what it's like. What are my neighbors like? Some of my neighbors. Yeah, I see a lot of moose, bears. Some years I don't see many bears. In this case, I just opened these boxes, was putting stuff away. I was in the yurt and I heard some noises outside. And I'm like, what is that? Nothing. Here's some more noise. I'm like, just ignoring it. And I'm like, wait a minute, I better look out there. So I look out and there's these brown bear cubs or grizzly bear cubs playing with these things that a couple of like buoys I brought back from the beach and these boxes. I'm like, oh, that's so cute. And then I'm like, what's the next question? Where's the mama bear? I'm looking around, don't see the mama bear anywhere, and I hear something under my yurt. Mama bear was under my yurt. And my bear spray was in my four-wheelers. So yeah, it can get interesting. And if you only remember the bears from this talk, I'm okay with that. All right, so back to sourdough. We took this GPR system out there the first time, looking at this bouldery surface, not knowing what's underneath. And I thought, this is probably a giant waste of time. But hey, we're out on a rock glacier in Alaska, so let's just do it. And so we took data across this part of the toe. And lo and behold, it was beautiful. We could see the bottom of a debris layer and this little echo that's right there running along under the surface about 3 meters down, all the way through. It's a little messy, but then we could see what was clearly the bottom of the glacier at 35, 40 meters down. Amazing. And so we did a bunch more lines, but it takes a lot of time. It's really slow going. This is what the surface is like, and these rocks on any kind of slope, they're moving. If it's wet, forget it. There's lichen on there. You'll be falling over and carrying equipment and stuff. So it is slow going. So we tried some other things. Oh, this is just a couple of weeks ago in the Eastern Sierras on a field trip. We got to a rock glacier, Bishop, California, to see if we could do a little preliminary work on that. Super bouldery. So former student Eric Peterson was like, hey, I love to ski. Let's just pull it on a sled when there's snow on top. And so he and another student at the time, Tyler Ming, went up in March and got out there, and there was barely enough snow, but they skied on the snow on top of the debris, on top of the ice. Worked pretty well, but you just can't always do that. So several years ago, I saw the USGS was doing some work with the drone radar, and I was like, I'm very skeptical of drones because I like to fly things I can sit in instead of to watch them fly. But it's like, let's try it out. And so managed to buy the system, the drone, the radar, and then we added a navigation system. Roberta added a pineapple can for scale. So you can get it, and it's out on the table outside, so you guys can see it when you're on your way out, if you didn't see it already. So I'm not gonna go through all the parameters, but 80 megahertz, remember that. So the idea is you fly over the surface, you gotta get through, you got tons in the air, you got debris, got ice and bedrock below. So it's a little more complicated than simply being on the surface, but, and I thought there's no way this is gonna work. No way, but it did. So this is the first trial. It's one of the early trials of sourdough, and Tyler's there checking on it to yell back to abort the mission if needed. And it's going down this really steep slope on the end that you cannot go down on foot. And that's part of the idea is not just quicker, but you can do things that are unsafe on foot. So a little zoom out so you can see the context a little bit. Yeah, it goes by. A little trail we made hiking from the woods. All right, comparison. You've got for that little segment close to that where we had some pulse echo, the surface-based data. The drone GPR, you can see the debris layer and you can see the base. Compared with the traditional ground-based system, which has stronger signal for sure, but we're basically seeing the same thing, which I was just amazed by. I really didn't think we'd see the bottom. I thought maybe we'll map the debris thickness and that's good enough. But in a lot of cases, we get the bed as well. So amazing. Switching to Wyoming, we've done a lot of work there, a place called Galena Creek. It was one of our 2 initial sites along with sourdough. This is a pretty big, I guess it's not too different from sourdough, but it had a road going up it for the mining days. Some of that road's gone now. Like this whole section, the rock glacier is just blows it off, kind of flowed with it. Still. So first time went up there with a class actually, and we did some data. We were able to use this system along one of these roads. I'm just going to show you some data from right in the middle. Pretty cool. So this is the data, and it's basically crossing from up here, curving on this road down to this lower place from A to A prime. And you can see some really nice signals in the data. I'm going to put up the interpretation next, just in the matter of time for days and time. But you've got the debris layer, you've got really clean ice, and you've got dirtier ice with layers. And there was an ice core, somebody actually managed to, or a core, they managed to drill into this back in the 90s, and they also saw ice down to this depth. So that was really cool to see how well that worked and to get the structure of the rock glacier that far down. High up in the SERP, it's really interesting up here. So this is way up. So if there's not really an ablation zone for these things, but they can have an accumulation zone. And so we were up here to see, like, what's going on up in what should be the accumulation zone, where you're feeding the glacier something. And this was really interesting. So ignore the big red squares. That was a different technique, but this little section up in the SERT showed these really, really beautiful dipping reflectors. So going high down to the lower part, high, low, alternating basically ice and debris, we think. And the other cool thing is where the debris layers come out, there's a little ridge on the surface. So there's a surface expression of these internal debris layers on the glacier. I hope you're thinking about Mars now, because that's the idea. It's like, maybe we can go from the ridges on the surface and infer what's below on Mars. So from this, this was from my former student Eric Peterson's thesis and papers. The idea is that this rock glacier actually grows by winter snowpack getting buried by rockfall events, and then preserved, because the rockfall will help preserve it through the next summer. And we're thinking that they correlate with climate cycles as well. So during periods where it's drier, there's more rock wall exposed, and less precipitation. The more rock wall is exposed, you get more rock slides and covers the ice more. And so that these alternating layers are representative of some kind of a climate signal that we'd like to unravel. All right. Of course, we're trying to, use the drone there. I want to show this one just partly because it gives you a better perspective of what the surface is like. How am I doing on time? Terrible. Okay. Not too bad, actually. So this surface, it's got a lot more undulations and changes, and really big blocks than we have in sourdough. So it was a good test of the drone. I just want to let it go until it pans around so you can see the view from up there, because the one in Alaska, sourdough, it's at like 2,500 feet elevation. This one's about 10,000 feet, from 9 to 10. So you're carrying a lot of equipment up at that altitude. It's a lot of work, but it's great. Beautiful place. There we go. Yeah, really nice. And we've got the drone flying a little grid here. And I'm attempting to fly the chase drone to take the video, and I'm really not very good at flying drones. So my biggest concern is crashing into this drone. All right, another quick example. High in the cirque, where it's really difficult to operate on foot, if you're steep. This is a different drone radar that's owned by colleagues at NAU, and we had them out in the field this summer to test it out, because it's lighter. It can go to higher altitudes, and we'd love to get one of those to do work in the Andes higher elevations, because our drone can't really go any higher than the other is. Oh, I forgot to hit the other one. So that's the following along, and on the right, this is sped up, looking at the drone from straight above. And this is the kind of thing you can do with the drone. There's no way you can do it on foot with these steep slopes, and it's just going back and forth doing a grid. So a lot of potential here. Also think about Mars. Like, you could maybe do something like this on Mars. And so we're testing these techniques out to see what works best. Photogrammetry, by doing these repeat photos over, multiple years, you can get it motion, and basically the software does image correlation of like the edges of boulders, get flow field over the entire glacier. And so as an example, for sourdough, the middle part of it is moving almost 2 meters per year. And then that's a little time lapse showing the difference between 2020 and 2022 for Galena Creek, showing the motion. And there's a whole lot of things we can do with this. I don't have a lot of time to get into it, but having the flow field is huge, because then you can put the dynamics of it to this internal structure in the surface wells. We can just look at surface elevation change by itself, and we've seen that the ones in Wyoming that we've been studying are dropping in elevation. The ones in Alaska that we've monitored aren't really. They're pretty stable in terms of their surface elevations. So some kind of a climate difference there. And then we're looking at internal layers, and once you have the velocity, you can start making assumptions about age. This might be, extrapolating a little bit much, but the idea is just to test it and see what age would these internal debris bands be if we extrapolated back in time. And so that's also like the holy grail for Mars would be like, oh, if we could get internal layering and somehow get ages, but that's probably beyond reach. At least for Earth studies, it's pretty interesting and could be very useful. All right, so almost done with that part. So what are our takeaways from all this? So it turns out a lot of places that were called rock glaciers really are debris covered glaciers, but we've seen a lot of variations in content. We looked at some in Colorado and the Rockies that are down around 20%. They're kind of dead, stagnant, and they're not really moving anymore. The debris layer, where ice content is high, is only 1 to 3 meters thick. There's internal layering sometimes, sometimes not. And we can see relationships between the surface morphology and the internal structure, the dynamics. And the next step is to put all this into a numerical model that you can then start playing around with and hopefully apply to Mars. And drone GPR is promising in terms of using it on Earth, but also for a technique for Mars exploration. So in terms of Mars, the next step, we've got so much coverage. These are tracks of Sherrod over these features, including Euripus Mons, which we were looking at earlier, that we've been able to do something called a 3D migration, which is common in the seismic industry, and build a 3-dimensional radar volume that you can slice in any direction, so you're not limited to the direction of the tracks. And my student Roberto Aguilar is working on that right now, and you can do 3D volumes. So this is kind of getting at what we did for Malaspina Glacier, but for Mars, getting a really nice holistic 3D view into these features. It's the first time this has been done for glaciers like this on Mars. And then, of course, we're really interested in instrumentation development. What could we fly on a drone? How would it work on Mars? What would it take? So that's the next steps. All right, real quick, Mark mentioned Snow for Flow. This is just a brand new NASA mission, just getting going. So I just wanted to give you a couple slides on that. It's NASA Earth Venture suborbital mission. We lead it, partnered with NASA's Goddard Space Flight Center, and the goal is to do better glacier projections across all of the Arctic, primarily by measuring snow accumulation with a high frequency radar sounder. So how much snow fell during the winter in the accumulation zone for a given year, and the ice thickness with the sounders that I've showed you, getting these like gates across to calculate ice flux. Then we'll have people on the surface of a handful of glaciers in each area to do validation measurements. And we're doing these because you can't measure these things from space. And in order to improve our projections, you really need these measurements. And that's what got us funded. We're going to Alaska, Yukon, Northeast Canada, like Ellesmere Island, that whole area, Southeast Greenland, and Svalbard. We're doing all that in 3 field seasons from March to May, or between 2027 and 2029. And we're going to be using the modernized DC-3 airframe. This gives us a lot of range. And it can fly really low and slow, which is what we need. I don't think we have audio, do we?
I don't.
Yeah. All right. Well, I'm going to skip this. It's a little intro to a video that AZPN did about this project. And it's really good. And it's not just because I'm in it, but because the cinematography is fantastic. And they did a nice job of the storyline. There's other people from U of A in it. And I just found out yesterday that it's nominated for a regional Grammy. So like the Rocky Mountain region Grammys. Emmy, sorry, not right. Emmy. I knew somehow that didn't seem right when I said it. All right, so anyway, I'll skip the little video part, but it's just really cool. But I will say you can use that or just go to the Snow for Flow webpage to learn more. But it's really pretty fantastic. It's clear. All right, I'm not gonna play it. All right, so thanks. Acknowledging funding sources, all sorts of NASA stuff, and U of A funding different parts of this, including just equipment, everything, startup, but all sorts of things. So really appreciate all of that. And then many students, none of this would have happened without all the fantastic students I've had. That's it. Happy to take questions. I'll stay as long as you want, answering questions.
Well, thank you, Jack, for a great talk, and sorry for the little AV glitch in the middle.
That's right.
Time to take a few questions, and then we're going to do our drawing for some of the books that we have.
So at the beginning, you said that like glaciers are further and south. Like, why is that?
Well, there's kind of a bit of a time lag between like a climate change and the glacier responding to it. And by the time they respond to it and equilibrate, the climate might change again. So it's kind of always tracking. And I think a part of the reason I say that is that since we've been studying glaciers on Earth, the climate has been changing. So we haven't been in a steady state. So they're all kind of reacting to the increase in CO2 emissions. The atmospheric warming basically is the main driver of that change. And so like what we're doing is comparing how do glaciers in different areas react to that, to try to understand how they work, you know, instead of just saying, oh, they're changing, like this is how much they're changing and why, and then we can do better. It's hard to find anything in nature that's really steady. Whether it's mass balance of a glacier or, you know, river systems or whatever, they're kind of always in some sort of flux.
Okay, any other question from the audience?
So you mentioned about in Mars changes in the axis of rotation that causes the variation in the glacier. So is that like the only process that could have caused this this phenomenon that we see, or could there be like ancient atmospheric events? Or
That's a really good question. That's probably the primary cause, but there could be secondary effects. One thing that the SHARAD radar helped us discover is there's a bunch of frozen CO2 ice sequestered in the south pole of Mars. And if say there's an obliquity swing, the ice starts moving from the poles. If that gets uncovered and released into the atmosphere, the amount there would double the atmospheric pressure on Mars, and that would really kind of accelerate those changes. Yeah, so there's things like maybe secondary effects that we're not that we're not totally aware of either. Yeah.
Amy, who's monitoring the online questions, do we have anything online?
Yeah, I have two questions. The first question is, at the 50,000-foot view, what are some of the strengths and weaknesses of using temperate rock glaciers on Earth as analogs for the cold-based debris-covered glaciers of Mars?
Yeah, that's a good question. So I think the gist of the question is, what are the pros and cons of using these terrestrial debris rock glaciers as analogs for Mars? encountered a lot of resistance to the idea when in the first 3 proposals I submitted to get this funded. But we finally got past it by collecting enough data to show that yes, there's water at the surface of these, like in the debris layer, but there's not, they aren't moving by sliding at the bed on water, because we got enough data to show that their velocity is really low, consistent with internal deformation of the ice like you would have on Mars. But water is an issue, and we still kind of encounter that problem. Overall, I think we're good, and it's hard to avoid on Earth. So that's one of the reasons we want to go to the high Andes to do more of this work. There's a lot of rock glaciers in the Andes. There's actually societal benefits to studying those as well, because they serve as water resources and buffers in the water supply for a lot of cities and agriculture in the arid parts of the Chile and Argentina. So yeah, I'm hoping we can. I haven't been able to get that funded yet either, but working on it. I think that, yeah, they're better Mars analogs, but I'm glad we've done all the work we have in Alaska and Wyoming and elsewhere to learn, get the techniques honed, because you don't want to be figuring that out when you're at 5,000 meters in the Andes.
So let's take the second question online, and then we'll wrap it up there. And Jack's happy to stay and answer more questions in person. But you say there was another one, Amy?
Yes, the other question is, are glaciers on Mars evolving differently because ice sublimates rather than melting?
Well, at the moment, the glaciers we're studying on Mars, they're not sublimating or melting because they're protected with this debris layer. So they're kind of stagnant. They're kind of relics, you know, like they're frozen in time, literally frozen in time. So we don't think that they're really undergoing those processes. I guess if you go in the past, when they're being formed, then that could have been occurring. And I don't know. I'd have to think about that. It's a good question. I don't know if, I mean, if you have mass loss through melting or sublimation, I don't know if it really matters. But if you have water melt at the bed, that really changes the dynamics, which you probably would not ever have at Mars. So yeah, good question. Would probably require a little more thought.
Well, while you think about that, thank you. Let's thank Jack again for his presentation.